Good morning, everyone. Good day. I'm Allison Hahn. I'm the other half of NE5, NE52. Can you go to the next slide, please? Okay, so in my office, it's all reactors all the time. We have all R&D related to the non-light water reactor designs over on our advanced reactor development team. And then we have on our reactor optimization and modernization team, all of the LWR research, including the existing fleet and small modular reactors. And then other programs such as integrated energy systems and advanced safeguards and security program outside the reactor building. So very high level. I think I only have 5 minutes and there's a lot to cover, so I'm going to kind of breeze through the next few slides. Can you go to the next slide, please? I do highly suggest everyone take a look at the websites. Each of these programs does have very nice websites. If you cannot find it, please just reach out to me and I can forward it to you. I don't think all of the slides have sites on it, but here's the first one, the Light Water Reactor Sustainability Program. The mission here, enable long-term operation of our existing nuclear plants and deploy innovative approaches to improve the economics and the economic competitiveness of the existing light water reactors. We do this through a combination of directly funded laboratory-led R&D, cost share, private-public partnerships with industry, universities, small businesses, and then with various stakeholders as well, including NRC, EPRI, and NEI. And you can see the focus areas here. We have plant modernization, flexible plant operation and generation, which are those non-electric applications, risk-informed systems analysis, materials research, tried and true, and then physical security, that is looking to validate methods and tools which can be used to implement an updated and cost-effective physical security regime. Next slide. So flexible plant operation and generation, integrated energy systems, it goes by a number of different things, but we have work here looking at non-electric applications for both the existing fleet and light water reactor sustainability program. And then we have on the other side of the house, the IES program for advanced reactors. And you can see here a really good graphic. I really like this graphic a lot, actually, that goes through the different products and applications that large LWRs, microreactors, small modular reactors, whatever their coolant is, can produce for the electric grid and the economy. So I really like this one. The integrated energy systems specifically conducts research development and deployment activities to explain the role of nuclear energy beyond just supporting that electric grid. And there's a number of applications here. We do have a number of hydrogen projects underway, private-public partnerships with industry to demonstrate the use of hydrogen at existing plants. And we're working on a number of directed R&D and university R&D to help support advanced reactors in this operating regime. Next slide, please. Advanced Reactor Safeguards program is working to address near-term challenges that advanced reactor vendor faces in meeting the U.S. domestic, I want to kind of underline that one verbally, domestic material control and accounting, and then the physical protection system requirements as well. And again, a number of different focus areas here. We have physical security. Here they're looking at new technologies and approaches to physical security, looking to reduce the upfront and operational costs, again, to improve the economics. Pebble bed reactor, MCNA approach is based around 3 item control areas. You've got the fresh pebble storage, the reactor and pebble handling system, and then the spent pebble storage as well. For combined microreactor, physical protection system, and the MCNA area, we're working to develop a domestic licensing framework for microreactors, really as a function of design options. Physical protection is a more challenging area for microreactors since they are seeking to develop that efficient physical protection system with limited on-site presence. The MCNA is relatively straightforward since most of these designs will likely use solid fuel assemblies or sealed cores that will likely be tracked as a unit. Liquid fueled reactor MCNA, an approach here is being developed based on staff level NRC discussions. More work is needed really to understand how inventories and radiation levels will vary with time. And then I know I kind of verbally highlighted or underlined domestic, but we are working internationally. A lot of these vendors will deploy domestically and internationally. And so by incorporating some of the requirements that the international community has now while the reactor designs are being developed, it'll really support those vendors in the long run and help with exporting those designs internationally. Next slide, please. Advanced Reactor Technologies program. Oh, I'm sorry, that got cut off. The program is supporting the development and commercialization of innovative, again, non-light water concepts by working with those external stakeholders, again, such as national labs, universities, industries, NRC, DoD, again, as well as international entities. And then within this program, we have 4 research campaigns. So first, we have the Fast Reactor campaign, which is focused on the development of technologies using liquid metal coolants and operating in the fast spectrum. The primary focus here is to de-risk and demonstrate fast reactor components and technologies, providing validated codes and experimental databases to support licensing, and then code qualifying advanced structural materials to reduce costs and increase those safety margins. The gas reactor campaign supports the development and deployment of high temperature gas reactors. These reactors operate at a very high temperature, 750 C range, because they are able to efficiently support a number of industrial applications that require those high temperatures, kind of bringing it back to that integrated energy systems program. This specific campaign is focused on alloy qualification and scaled experiments, again, to support design and licensing. And then we have the molten salt reactor research campaign. This provides support for 2 variants of the molten salt reactor. One has the fuel dissolved in the molten salt coolant, and one which uses the solid TRISO fuel. The MSR campaign is focused on investigating fundamental salt properties, materials, models, and fuels to support both of these kinds of reactors. And then finally, the ART program supports the development and future demonstration of microreactors. And here there's a number of different activities, including the MARVEL reactor that's being designed and demonstrated at a national laboratory. Next slide, please. So I mentioned TRISO a second ago, and I'm sure most of you are aware of TRISO, but it is a robust fuel form that has demonstrated excellent safety performance for high temperature nuclear applications. And again, because of this, numerous companies are pursuing the use of TRISO fuel in their advanced high temperature reactor concepts. And a lot of times, TRISO fueled reactors are, they utilize graphite as a moderator and fuel matrix. And so the graphite development is really occurring in parallel with the development of TRISO fuel itself, at least within our national laboratory complex. Since 2004, the Office of Nuclear Energy has been supporting the TRISO fuel qualification program. It has included a number of irradiation experiments followed by that PIE to generate the data needed to really enable the vendors to develop and license the reactors that they plan to use TRISO with. The TRISO fuel qualification program also developed fabrication techniques for TRISO fuel, which is helping to establish a domestic commercial TRISO fuel fabrication capability. And then similarly, the graphite qualification program includes a number of irradiation experiments, characterization, and PIE of existing nuclear grades of graphite. The graphite qualification program aims to qualify nuclear grade graphite and establish design rules for use in high temperature gas reactor cores. Next slide. Sorry, I'm going so fast. We lost the title, sorry. So this is our Advanced Reactor Regulatory Development Program. The previous slides were kind of specifically focused on reactor-specific R&D, but we have programs that support R&D outside the reactor pressure vessel too. The Advanced Reactor Regulatory Development Program coordinates closely with the NRC and industry to address and resolve key regulatory framework issues that directly impact advanced reactor demonstration and deployment. And a key part of this program has been supporting an industry-led project to develop proposed guidance for an NRC license application through the Technology Inclusive Content of Applications Project, or TCAP. And so this project was really built on the outcomes of the licensing modernization project prior. I'm going to go to the next slide So the National Reactor Innovation Center, um, again, we went through R&D, regulatory development. This program really lends itself to providing vendors with access to capabilities and expertise at the national labs, and really that unique infrastructure needed to demonstrate their pre-commercial design. So this program is led by Idaho National Laboratory by providing a range of capabilities to support nuclear technology demonstrations, including the establishment of demonstration test beds. The test beds will provide that infrastructure where developers can actually come in and demonstrate and test their technologies, such as a fueled test reactor, obtain the data that they need, and then support the design and licensing applications as they move forward. So the first one is the demonstration and operation of microreactor experiments, or DOME. Will support demonstration of microreactor technologies and is expected to be ready for the first test by 2026. And we are also working on a second test bed, which can support experimental reactors that use safeguards Category 1 materials for operation. And again, although not required for commercial concepts, some reactor demonstrations and experiments require that higher enrichment fuel to keep the size of this test reactor, this experimental reactor, small, while ensuring that the neutronics and thermal hydraulics are representative of the larger commercial designs. And so this requires a specific space to be able to do that. And then lastly, NRIC initiated the Advanced Construction Initiative, Advanced Construction Technologies Initiative, last year, which is looking to reduce some of those cost overruns and schedule slippages that have really been evident in construction of nuclear plants recently. So NRIC, in collaboration with some industry partners, will develop advanced nuclear plant construction technologies that can hopefully drive down costs and speed up the pace of advanced nuclear deployment. And next slide, I think, is my last slide. So I can answer any questions or head on to the next one. Thank you.